In this video, we're going to connect from machine learning to local large language models, those that we run in LM Studio and similar. Hopefully by the end of this video, you're going to understand some more of what we've been talking about with that machine learning and connecting those dots to what we need in order to get to large language models. A large language model, often shortened as LLM, is still a machine learning model. It's nothing magical, nothing mystical than what we did in, say, Python before. An LLM is an algorithm that learns patterns from data. What changes is the scale and the training style. Traditional supervised learning requires labels. We feed a model rows of data and we feed the correct answers in. For example, this network connection is normal. This network connection from the log file is an attack. The model studies those examples and tries to reproduce that mapping. An LLM skips the labels. It trains on trillions of words gathered from books, web pages, and code repositories. Its task is deceptively simple. Predict the next token in a sequence. If the text says the firewall blocked the model learns that the next likely word or the next likely token might be connection. The firewall blocked the connection, in other words. Do that prediction billions of times and the model begins to absorb grammar, tone, and world knowledge. That's self-supervised learning. The model learns from the data itself. So in spirit, LLMs are the same as any other machine learning system. They find patterns and make predictions, only now the input is language and the output is language as well. When we type a sentence into a model, the model itself doesn't see letters or full words, it sees tokens. A token is the smallest chunk of text that the model understands. Sometimes it is a full word. Sometimes it's just part of a word. Sometimes it's punctuation. Sometimes it's a space. All of those infer meaning in grammatical context, and they infer meaning in an LLM context as well. For example, the word firewall might be split into two tokens, fire and wall. The phrase connection refused would become three tokens, connection refused and the period after it. Every model has its own tokenizer, a kind of secret decoder ring that decides how to slice text. When you hit enter, when you're using an LLM, when you're using AI, that tokenizer converts your words into a long list of numbers representing those tokens. The model predicts the next token, appends it to the list, and repeats over and over until it finishes a thought. If you watch an LLM stream words on your screen one at a time, that's exactly what's happening. Each new token is a single guess that came from the words before. Of course, computers can't reason with words directly, so every token is transformed into a vector, a list of numbers called an embedding. Embeddings are where meaning lives. Words with similar meanings end up in similar vectors. If you plotted them in 3D space, malware and virus would sit close together, while coffee would be far away from malware and virus. The model doesn't memorize dictionary definitions, it discovers relationships based on usage patterns. If port scan and suspicious traffic often appear in the same context, their vectors drift towards one another. That numerical geometry allows the model to do something that looks like reasoning. It can infer that cyber attack is related to intrusion, even if those two words never appeared side by side in the training data. So whenever we talk about an LLM's understanding, what we really mean is the structure of these embedding spaces. Now let's talk about memory, the model's context window. Unlike a human, an LLM doesn't truly remember the entire conversation. It has a sliding window of recent tokens, perhaps 4,000, maybe 8,000, or maybe more in advanced models. Anything inside that window is fair game for prediction. Anything outside that window simply vanishes. Imagine you're reading a chat log through a narrow window that only shows the last few pages. If you scroll forward, earlier pages disappear. That's exactly how an LLM experiences your prompt. When your input grows too long, you'll notice that the model starts to forget earlier facts. It's not being lazy. The information literally fell out of scope. It's like it never knew it. Understanding context length is essential when we build prompts for security data. A model with an 8,000 token limit can only handle about 5 pages of logs at once. Longer sessions require some summarizing or some chunking, some splitting it up before feeding it in. Every time an LLM chooses its next token, it looks at probabilities. Some tokens are highly likely, others are less so. Temperature and top-P or top P are the two knobs that decide how adventurous a model will be. At 0, the model always picks the most probable token. Predictable, factual, maybe a little stiff. At 1 for temperature, the model predicts some creativity, and at 2, it's like caffeine and chaos. The model starts to improvise. Top-P or top P is sometimes called nucleus sampling. It limits how far down the probability list isn't allowed to look. Top P at 0.9, the model only samples from the smallest set of tokens whose combined probability is 90%, ignoring the long tail of weird options. Together, those parameters are the creativity controls on an LLM. For cybersecurity analysis, we keep temperature low to ensure consistency. For brainstorming or for summaries, we might turn it up and let the model sort of be a little bit creative with those summaries, or at least creative in its word choices. So far, we've talked a lot of theory. Now let's bring it down to earth with LM Studio. LM Studio lets you run open-weight models directly on the machine. There's no cloud connection needed once you download the model, and no data upload. Everything happens locally. So why is that a big deal? Well, because privacy and accessibility matter. If you're analyzing sensitive network logs, you don't want them leaving your system. And LM Studio helps to bridge that gap. It provides a friendly interface for local experimentation. Each model name hides a number like 7B or 13B or 770B. Those letters stand for billions of parameters, the internal weights that the model learned during training. Think of the parameters as neurons in a brain. More neurons usually means deeper understanding, but also heavier hardware requirements. Running a full precision 13B model might demand 20 gigabytes of memory. That's too much for a typical laptop. Now that's where quantization comes in. Quantization compresses each weight from 16 bits or 32 bits down to 4 or 8 bits. It's like saving a high-res photo at a smaller size. Slightly less detail, but far less storage. A 7BQ4 model often fits in well under 5 gigs of RAM, and so that's perfect for a lot of the things that we do day to day when we need to work with a local LLM. Many of you are familiar with prompting already, working with AI models. In traditional programming, logic lives in code. With LLMs, logic lives in your prompt, and your prompt is essentially like the program. So a vague instruction like explain this log leaves the model guessing as to your intent. But a precise instruction like classify this log as normal attack and give one-sentence reasoning sets clear boundaries for the model. Good prompts share 3 traits: context, clarity, and constraint. Context tells the model who it is. For example, you're a cybersecurity analyst. Clarity spells out the task, and constraint defines the desired format or length. For even better results, we can use few-shot prompting, providing 3 or 4 labeled examples, and then ask the model to continue the pattern. This technique mimics how humans learn by analogy and works surprisingly well for short classification jobs. Let's look a little deeper. We already discussed it slightly, but let's look a little deeper at why local models matter. Privacy is important. When we analyze log files in cybersecurity, we're dealing with sensitive data. IP addresses, user IDs are in there, sometimes confidential host names. That local inference keeps the data on the local machine. Second, experimentation. It allows us to experiment with parameters freely without worrying about any API limits or cloud costs or anything like that. If we want to test different temperature settings for the model, we can definitely do that and not lose. It'll only cost the time that it takes to run those prompts. Third is insight. Watching the local model's speed and memory usage teaches you what those abstract numbers actually mean. You'll see, for instance, how a 13B model feels slower but produces richer answers than a 7B one. And finally, running models locally empowers you to work offline, which is an underrated advantage in cybersecurity because we can be completely offline in an air-gapped environment or in a secure environment where we don't have an internet connection. So this short video provided some detail into large language models, or LLM. They're an evolution, not a revolution, of machine learning. They still learn patterns, they just learn from them from words instead of numbers. Text becomes tokens, tokens become embeddings, embeddings become predictions inside of a moving context window. Temperature and top P control how deterministic or creative those predictions feel. And LM Studio makes it possible to experiment safely on your own system using open weight models. So hopefully you found this video to be helpful and useful, and we'll be looking for you in another video coming up. Thank you for watching.